Okay, now let's design a deep foundation with pile caps. And as explained in previous clip, we have a D columns, which is piles, and we need to have a cap to fix them and combine them. Acts as a one structural systems. Designing and installing a pile cap is inevitable. Okay, the number of piles, which is denoted by N, is equivalent to the foundation area of the shallow foundations. You calculate shallow foundations, you don't use a factors. You just use a service load, if you remember. Go back to and review it if you can remember. So number of piles is dividing all the service load from on the piles divided by the pile allowable capacity. This used to be a allowable pile bearing capacity, if you remember. Right now it is a pile capacities on one pile. Okay, and this will get you a number of piles. Once you get number of piles, then you can calculate now bearing pressure on the pile or pile pressure on the pile using a factored load. Factored load, right? So RU is pile pressures that we need to design against. So this RU is the pile force provided by one pile, which is very important, and where you have to use a factored load. This was what pile bearing pressure on shallow foundations as well. So the concepts are same with the different parameters, right? Number of piles corresponds to what shallow pile area, and RU was equal to pile bearing pressure, not capacity. All right. Okay. Now let's take a look at a example. We have here dead load. We have here live load, and all concrete we use 24 megapascal and 400 megapascal rebar, and we have a soils weight 2.5 tons per cubic meter, right? And also the pile capacity on one pile has given as a 35 ton or 350 kilonewtons, right? Okay, all these given loadings, now we design deep foundations. Now we have to calculate how many pile we're gonna need to support these loadings given right there. Okay, here we have to divide all the loading on the pile divided by what? Pile bearing capacity on one pile. And we use a service load, which means that we don't use factors. And this is what we have from problem statement without factor applications. So we need almost nine piles. Okay, first of all, I'm gonna start with 9 piles. If necessary, we can revise this number of piles that we need. All right. Okay. If you arrange 9 piles, as you see over there, and we have 3 layers of 3 columns at each layer, something like that. And we need to calculate pile force, which means that a force thrust of lift force by piles, and we need a factored load here for design, and we end up 47.9 tons, which is acted by one pile onto the foundation. So 9 piles and 10 piles, each 47.9 ton is gonna push up and try to break the foundations. Here it is foundation called a pile cap. Okay, it is a pile cap. And so all pile cap has to be designed well to resist these 47.9 tons provided by each pile. Okay, we're gonna start with a two-way shear, and all these things are similar that we see for shallow foundation. To shear capacity of a pile cap. This is pile cap, right? This is the little concrete block that fix all deep piles and help them to act as a one foundation systems. Okay, we have a two-way shear where we can calculate based on failure parameters right here. Okay, these failure parameters are determined to d over 2 from the face of column. They are same as the two-way shear for slabs and shallow foundation. Okay, so the B0 summation of failure parameter or critical parameter is nothing more than a 60. This is 60, and this is 30 d over 2. This is 30 d over 2. So we have a 60 plus 6 times 4 parameters, and we end up on the 80 centimeter here. Okay, and we have a punching shear out of the parameters, critical parameters. Okay, so all the piles, how many piles is going to contribute to the punching shears on this pile cap? So 1, 2, 3, 4, 5, 6, 7, 8. 8 piles will push the pile cap up outside of these parameters. This is a punching shear. So equivalent to punching shear to this punching shear provided by 8 piles, 8 deep piles is similar to one that provided by the shallow foundation as well, if you remember. All right. So the punching shear is given by this value, 47.9 times 8. 8 is number of piles that contributes to punching shear. So we have this value, 383. And now we have to calculate the two-way shear capacity, and they are exactly similar to one we saw for slabs and foundation, shallow foundation as well. And I'm not going to repeat the theory behind it, but just use a appropriate formula. All right, you have to go through selecting one of the three equations and choose the minimum. And this is the formula they want to stick to calculate two-way design shear capacity. Right here, B0 is coming from here, and all these parameters are easily found from problem statements. And we have a 402 as a shear capacity of two-way shear of the cap structure, and which is greater than what's been calculated with the punching shear. This is affected punching shear there, okay. And we can take a D of 60 centimeters, okay. So 60 centimeters of depth of cap structure should be okay. Now we calculate one-way shear on pile cap, and how many pile is gonna break through in one-way manners. Here, 3 piles, actually half of 3 piles, isn't it? Because this is half, this is half, this is half. And try to break through the cap foundations, cap structure with the one-way, right? So we have here one-way critical sectional one-way D from the face of columns here. So that this is 60, and we have a 1A critical plane over there, right? Okay, now what is the load, shear load by 1A action? Is this, and times 3 and half of it, right? Half of it. So, okay, see you here. What is load for one-way? Okay, here you go. 47.9 times 30, half of it, right? There are 72, around 72 ton, and this is the formula for one-way shear capacity. Again, with the P factor, everything is very familiar with this in these equations, right? So you got this, should be okay too. So we don't have to worry about both two ways and one ways. And don't forget to calculate the shear capacity and compare that with the shear force on one pile at each pile level. All right, at each pile level. So this pile, each of them will also try to break through the pile cap structure as a shear force and punching force. So what is that? Punching force provided by this one pile, and that's a one pile force, right? We calculate here. This is pile force provided by one pile, right? And then the critical section for one pile is easy again, and the critical section is gonna be d over 2 from the face of the pile here, right? Okay, so this is a pile diameter and d over 2 here and d over 2 there, right? Because and actually this is a 90 diameter, and the parameters of this circle is this. Okay, and this is 282.6, and that's gonna be plugged into this right here to calculate two-way shear capacity. This is design shear capacity with the three factors. Try to resist against a punching shear provided by one piles, and this is just simpler calculation than the entire shear calculations, entire punching calculations, right? Okay. Now we have here, this is a shear capacities, and we have a one shear force on one acting on one piles is will be greater than this value, right? So two-way shear, considering a one pile failure criteria and failure parameters, now is greater than the shear force provided one piles. So we are all okay. Two-way shear, one-way shear, and two-way shear by one pile. All right. And the last item that we need to go and calculate is the fractional resistance and levers to resist against the bending moment provided by each pile force. Okay, so if you see the piles, how many piles, these three piles is gonna create a bending moment against this part of the pile cap, right? So the acting face is the face of the column, as you know. So how many piles will contribute to bending moment? One, two, three, right? And the moment arm is probably from here to the center of the pile, each pile. So we calculate it, and from here to center of each pile is easy to calculate. From this distance, from this distance, from this distance, from here, right? So what is that? That is a simply 0.6 meter. Okay. So why don't you calculate if you can get a 0.6 meter? So I don't have to really worry about verifying this value for you, right? Okay. So we're gonna use a 0.6 without further verifications and easy, and 3 times and the pile force on each pile times the moment arm. So this is the moment that we have to take care of, 86.22, right? And it's easy to design or calculate lever ratio on based on this moment, and we get end up this, and we can use 11D25, whose area is a 55, which is greater than the required, right? And of course, we're going to have these 11 bars in both directions, because you're going to have a moment contributed by the pile in both directions. In this way, we have this pile is going to break through the pile cap structure upwards, and this is going to act on the pile cap upwards. Right? So we have to have a two-dimensional type of reverse. Okay, now we place rebar that way, and we have D, which is 60s, and everything is given, right? This is how you calculate the foundation. It's nothing more than a calculation, shallow foundation for cap structures. But this design of a deep foundation is very similar to design of the shallow foundations. Okay, let's design a deep foundation with pile cap in different way. In this particular example, we will assume the number of piles instead of obtaining number of piles directly. Okay. All this loading, service load, service moment. Oh, okay. One thing is really different from previous examples is that we have a overturning moments here. The column is subjected to overturning moments in both axes, right? But this is a mostly different from the previous design examples and very significant to understand. Okay, let's take a look at example. Here we assume number of pile foundation, this is somewhere 12, right? Well, you can calculate this, but when you have a overturning moment, it's not convenient to calculate number of piles directly. So we just assume number of piles, which is M12, right? And here we have a two terms contributed by the overturning moment, right? All we understand the formula P of A. P of A is from a actual load, and my over I here in x direction, y direction, or whatever, x direction, or y direction, whatever is coming from a overturning moment, which is shown right there. Okay, then this term is going to be more simplified when we consider the moment of inertias. So moment of inertias are, as you know, a moment of inertia column itself, and we have to add the extra terms that we see additional moment of inertia when the moment of inertia is going to transfer to the original center of columns, right? So, for example, if your axis of moment of inertia here, your columns over there, then you have to calculate your moment of inertia of the column itself, I0, right there. And then you go and have to move this structure to the axis of moment of inertia, which is defined by x, for example. Then you have to consider extra terms which in which you calculate a times x squared, right? X squared. Okay, so this is all you have. Okay, now let's take a look at calculation of moment of inertia of the column with the axis outside of the member. First of all, we need to calculate moment of inertia of column itself at here, I0. And then we have to transfer this to the axis of moment of inertia, right, with the distance xi and area of column A. Then we have to add the extra terms, which is defined by the A. Then we have to add a extra term, ax1 squared, to the I0 to transfer the moment of inertia to the axis of moment of inertia, right? And if you see right there, this I0 is very small because we have to calculate pH cube, and which becomes very small compared with this value because L is meters and HBs are centimeters and millimeters, right? So we can just simply ignore this term, ignore these terms. So we just end up with AX1 square, AX, A distance squares, right? And understanding this, if we multiply, okay, I now become a AX square, right? And multiply A in both sides of the equations, we have A, A cancel and right side. So we have is force P sigma NA becomes force P on the left side of the term. Force P becomes My over X1 square, right? So look at that. So sigma A becomes this, and this is nothing more than a force, okay? So now here we have this equation, that's right? Force P is a P over N and the number of piles and the force per each piles, and this is a force contribution. It's not moment anymore. This is force contribution, right? This is force contribution. It's a x-axis and the other direction, x direction, the other directions. Okay, and of course x and y indicates the distance of the center of pile to the axis of moment, right? Axis of moment of inertia. Okay. All right. Now we have all the value. These values are given in problem statement. I'm going to plug into this equation and to get a. We calculate P. P is here. This is service when you calculate the number of piles, and we increase to 10% to take care of all the extra loadings and self weight and surcharges on the piles, so on and so forth. Okay, and moment is also 30 plus 20, which is unfactored, and we assume n is equal to 12, and also x is distance of the pile from the axis of moment of inertia. So here, x is nothing more than this distance from here up to here, from here up to here, right? We have two in the first column, line, and xi from here to here, and x2 line from here to here, right? So, okay, let me see more clearly the other diagrams. Okay, here you go. See here, from here to here to here, and from here to here, right? Okay, what is that length of it? The first one is, okay, what is the first one? Fourth length to the first line of pile is 450 millimeter, right? 450 millimeter from here to here. And the distance from the center column to the next line of piles, go here, we add 900 more, it becomes 1.35 meter, right? Okay, so we can calculate xi, summation of xi square. We have 3.45 square meters and 1.35 square. So, and times 2 on both sides of the pile cap, right? Both symmetrics, right? So we have this, right? So we're going to put this 12.15 in here, right? We just consider in one direction only, in x direction. So we put them here, right? So P max, we're going to end up here 23.9. And we have to compare this P max to what? To the pile capacity of one pile, right? This is a pile loadings on the pile. And if loading on the pile is less than the pile capacity, which to say pile capacity, that's okay. Now it's given 25, so we are barely okay, right? So now this is a calculation of a pile force, assuming a number of piles and 12. So if you put this value right here, it's nothing more than a calculating number of piles. So that is why we don't use a load factors here. All right. So don't get confused. This is very tricky and confusing, but it's okay. Now we verify that number of 12 number of piles for supporting this loading condition looks okay, right? And we're going to design the pile caps and piles everything. Right here, now we have to calculate pile force that is provided, that is caused by one pile. So we need a load factor here, load factor, right? And we need the load factors, all that. Now we have this new load factor the actual force, factor the moment, right? And we're going to calculate a combined force provided by one pile. And given the situation where, as we know, we have a factor the load here, factor the moment, right? So we're going to calculate here. So we have a plus minus value because if we have a moment distractions, then you're going to have a tension over there and compressions over there. And you're going to go this way, we're going to have compression right here and tension in this portion. So this is going to be alternating. It doesn't matter. So we're going to just one direction and calculate minus plus so that we have a assuming this way, we have all tensions right there, we have compressions right there. So the line, the pile line in this region is going to contribute the tension each. This is a minus, okay, minus, and this is further line of columns and the minus tension for the near line of columns, right? This is plus indicates that we are in the compressions with the near column line and the far column line, right? So we have all the column forces per each pile, right? So these are small force for near columns and big force for far columns here, okay? And the reason also is going to be very big right there. It's going to be added on the vertical force, right? On the compression side. And it's going to be subtracted from tension side, right? So all the values, even in tension side, are positive. So we don't have any tension column so far, but we may have tension column there when overturning moment is greater than the actual load, right there. Okay, so we don't have tension piles, but we have a force compression side and tension side, and compression side. Now let's try to calculate and design the pipe caps. The pipe cap also needs to be checked against one-way shear and two-way shear. Okay, one-way shear is easy. So what is the force that causes one-way shear failure? Caused by these three piles, right? When three piles thrust the pipe cap upward, then we gonna have a one-way shear failure conditions right there. So what is the shear force for that? We have three forces, right? One, two, three. Okay. So we just try to pick up a big number, the biggest number. We can pick up any number, but it makes the design most conservative. 333 is going to be times 3, and we have a 99, right? So this is a one-way shear failure. Okay. And what's the shear capacity for one-way shear? As this, right? So I'm going to give you a little thinking point, right? Okay, take a look at these coefficients over there. We use a 0.53 instead of 1 over 6. So we have increased a one-way shear pile capacity a little bit because we have a concentrate loadings on this pile cap instead of having a distributed load as we used for slabs and shallow foundation. So we gonna be have a little more benefit from this change of coefficients. Okay. Now the capacity, one issue capacity is this. So we okay. think we're okay, right? Greater than this one-way shear induced by three piles. Okay. And we're going to go and take a look at two-way shear. Two-way shear is this, right? Is this? This is a critical sections for punching shear, and how many piles contributes to the punching shear is going to go and make a hole on the pile caps in the middle. We have a 8 here, and 9, 10. So 10 piles is going to contribute a punching shear failure if there is any. All right. So the whole entire punching shear is calculated on this, right? And then the failure, critical failure, is this 66. And again, it is a d over 2 from the face of columns, and I'm not going to repeat that. So we have here the peripheral length of critical sections are this, okay, and all this calculated based upon three equations as we explained, and we chose this and end up with a this value 376, which is greater than the two-way punching shear right there, so we're okay. And I don't have to explain, do I? All these numbers are plugged into properly, okay? And now we checked a one-way shear, two-way shear, all that, right? And also don't forget to check a two-way shear for single column. So I think we're gonna omit this because that is a trivial, all right? And now we are ready to calculate the lever that resists the by the pile force. Okay, so what is the force anyway induced by pile due to um, moment and vertical load? Moment by the eccentricity of the columns. Okay, we have here three piles contributes moment, bending moment, and another three piles contributes another bending moment with different moment arm here, very short, and from here to here, right? Okay, so we just take a look at that and use in here, right? In here. So three columns, and three columns. It's in near columns. This is four columns, right? So verify these dimensions. Well, that's easy. So we end up with mu. We end up with mu. And following your knowledge that you learned in RC class, we end up with a 15, 22 diameter levers on pile caps in each directions, right? And this going this way and another going that way, right? So we need a both directions. We need a both directions. Okay? And probably we have a different moment, bending moment in here. Okay, yeah. We have a different bending moment because they are installed, the piles are installed differently in x-axis and y-axis, right? In this way, we have four columns in one line, just each line, one here, one here. So we have a bending moment diagram contributed by these four piles with the distance from here to the center of the pile. So this here and center of the pile, you verify it, please. And they are this, where, here, I guess. Okay, this is what you get in the other directions. Okay, you verify this number, but I simply adapted four columns with a moment arm measured from the face of the column to the center of the pile. Okay, moment arm measured from the face of the column to the center of the pile. Okay, I think that is the easiest thing to do to calculate bending moment diagrams on the other directions. Okay. So you're doing same thing and find out lever that is a 14 levers at 22 diameters, right? And this directions, okay? And here, now briefly take a look at if you have enough length for developing these fractional levers, okay? And this is LDV is calculating to give you a basic developing length. In here, you need a 92.3. And depending on your conditions, alpha, beta, gammas, and I'm not going to go through, but you can use A1 for these coefficients. And so you're going to have end up 77 centimeter, which is required as a basic length for development. All right. So you're going to take a look at a appropriate chapter from undergraduate RC class, which is very important, still applies in foundation and pile cap. And you're going to check if you can provide the distance or a space which is greater than 77 centimeters, because 77 is required for your lever to be extended, right? So if you take a look at a short dimensions right here, okay, this. So your lever from here to here to be extended at least equal to or greater than 77 centimeter, all right? So we'll see calculate if we have enough length for that. And this is a 2.7 meter, and then we have to subtract a column dimensions and divide by 2. All right? And you're going to give this entire distance from the face of column to the end of the pile or pile caps. And we need some 8 centimeter, 7 centimeter to be subtracted for a cover. You need the cover, right? Cover means you need some lever stops before some distances to protect lever from the collisions and icings and all the environmental situations. Okay, so we try to keep that 8 centimeter from the edge of the foundation where you have this 97 centimeter left, right? So this 97 centimeter, you have enough space to have a 70 centimeter required by the basic developing length, all right? So you're okay. So this is probably your design details and construction document, and people will construct based upon your construction document as shown there. We have 3 piles, and we have a levers differently placed in both directions because your pile arrangement are not symmetry anymore, and we have some developing length checked already all there, right? It's beautiful, right? And we see this how to design this splicing length from dowel to column levers. So same theory for that applies here between columns and pile caps, and everything's under control, right? And probably next clip we'll take a look at now the foundation associated with a soil's properties and construction characteristics. We're going to take a look at how we're going to get a pile capacity to be ensured when you construct the piles, when you're driving piles, right? And this driving piles and try to ensure the pile capacity that's been calculated in design. For example, here, what is your pile capacities that you need to really ensure in pile constructions here? Because you are going to have at least this right here. Okay, where is it here? Here you go. 25 ton per piles, 250 kilonewtons. So this pile capacity should be ensured. You have to make sure that your constructions possess this pile capacity. Why? All your pile foundations, including deep piles, including and pile caps and levers, everything based on this very important parameter, which is 25. Is that number means it is a pile allowable pile capacity per pile. So when you don't have a pile, when your soil cannot provide you 25 tons per pile, when you drive in it, when you constructed it, you'll be in big trouble, right? So you have to go in deeper and deeper and deeper until you see your pile capacity is realized, right? So if you can go less, if you can have a 25 tons easily, then you can start right. So the length of piles really depends on soil conditions. You can go deeper and deeper and still cannot have 25 tons, but whereas you can go and shore and shore and you can get 25 tons of pile. It depends on your soil. If your soils are very stiff and very high SPT values and high cohesion values and friction values, and it is favorable for having a pile capacity at shortest depths. Otherwise, you have to go deep in the soil foundation soils to get a allowable bearing capacity on one file, right? This is very important. And this is something that really we don't learn in school, but you want to take a look at it, get familiar with that practices, right? So next, very clear, we're going to take a look at a pile load test. There's two way for pile load test. The first way is a static load test, right? Static load test, and the other way is doing dynamic load test. Dynamic load test. So static load test, dynamic load test is the test that you need to make sure that your piles can be supported by the soil with the allowable pile bearing capacities. Okay, and especially when you do pile dynamic test, we're gonna use a PDA technology, PDA technologies, and it's gonna be really important and fun. And the PDA is very flexible, useful way of doing pile dynamic test to verify your pile bearing capacities.